Hello, I'm Mr. Clark and I'm going to teach you today about how to do some KP calculations. So we're going to have a look at one of the questions from your problem sheet. We're going to go for example D and have a look there. So I've written the question out. It's 1 mole of sulfur dioxide and 2 moles of oxygen are left to equilibrate at 200 degrees C in 2 atmospheres. The equilibrium mixture contains 0.5 moles of sulfur trioxide. Determine Kp. So Kp is quite similar to Kc, except now we're talking about pressures. So what you can imagine is maybe there's a big flask that is sealed, and inside is some sulfur dioxide, some oxygen and some sulfur trioxide, and they're going to be left to react together and form an equilibrium mixture. But to begin with, all there is in there is 1 mole of sulfur dioxide and 2 moles of oxygen and no moles of sulfur trioxide. So we're going to use the ICE method. That is the initial, the change and the equilibrium amounts. So the question says that 0.5 moles of sulfur trioxide is formed, so that's gone up by 0.5, and the final amount there is 0.5. Now that's affected the amount of reactants used up. So because there's a 2 in the stoichiometry here, this increase of 0.5 is 2 lots of it, so 1 lot of it is 0.25. So oxygen would have gone down because it's been used up by 0.25, so its equilibrium moles is 1.75, and sulfur dioxide will have gone down by 0.5 because there's a 2 in front of it, so the equilibrium moles of that is 0.5. What you need to do next is work out the mole fractions. So of the total amount of moles here, which is 0.5, 1.75, 2.75, how much is each worth? So just a quick bit of maths there is 0.5 over 2.75 is 0.18 recurring. Let's just leave it like that. For oxygen it is 1.75 over 2.75, which is 0.63 recurring, so let's do 6363. And for sulfur trioxide it's the same as above. So now we've got our mole fractions. So we've got our mole fractions, we can work out from the total pressure of the vessel how much each partial pressure each one exerts on the system. So the partial pressure of sulfur dioxide will be 0.1818 times 2, which is let's say 0.364, and oxygen will be 0.6363 times 2, let's call that 1.273. And sulfur trioxide will be 0.1818 times 2, which is 0.364. So you've got your partial pressures. Now we can plug these into our Kp expression. So let's write an expression for Kp, and it's exactly the same way as you do for Kc, but we're very picky about how we write it. We're not going to use square brackets anymore because it's not a concentration. So we're going to use a P in a rounded bracket and then a subscript SO3, but that is going to be to the power of 2 because this is to the power of 2. 2 lots of it. So that's going to be over the partial pressure of sulfur dioxide squared times by the pressure of oxygen. Okay, and that is your equilibrium expression for Kp. So now it's just a case of crunching in some numbers, and what we can do is let's do 0.364 squared over 0.364 squared times by 1.273, and then that should equal 0.786 to 3 significant figures. Okay, the next thing I like to do is work out the units. I always do that a bit separately. So if the question gives you pascals or atmospheres or bar, just keep that and don't do any conversions, and we just use that as your final answer. So let's have a look. Just crunch out the units. You've got 2 atmospheres here, atmospheres times atmospheres. So we can do atmospheres times atmospheres over 1, 2 because it's squared, 3, so over 3 lots of atmosphere. And you got that. If we cancel those down, you're left with 1 over atmosphere, which means your unit is atmospheres to the minus 1. So we've got our final answer, which is 0.786 atmospheres to the minus 1 to 3 significant figures. And that is how to do a Kp calculation. Thank you for watching. Stay safe and take care.